Welcome students to the online learning video lectures. The course is differential equations with course code MAT18R4031. This is unit 2 of block 5 from Department of Mathematics, Kalasalingam Academy of Research and Education. So let me come to the topic. So as you know, in block 5 we are discussing second order PDE. So in the previous video lecture, I was introducing second order PDEs, and also I have discussed the classification of it. Now in unit 2 there is a special type of second order PDE called as second order PDE with constant coefficient, and I missed one part. I would like to second order linear PDE with constant coefficients. So how it looks like, let me take. So before I describe how it looks like, let me introduce some well-known abbreviation. We already know that P denotes del z del x, where z is the surface integral. Q denotes del z del y. Again, further in second order differential equation, we will be writing this also. R denotes del 2z del x2. Then S denotes del 2z del x del y, and finally what T denotes del 2z del y2. Then the second order linear PDE is of the form, okay, let me write one by one. Capital R, okay, I don't want to write capital R because I introduced with A, so I would like to write it this way: A into small r plus B into small s plus C into T plus D into P plus E into Q plus F into Z equal to G. Okay, where A, B, C, D, E, F and G are all constants only. So you can see that the heading was with constant coefficients, which is justified. Okay, so all the coefficient of the derivatives, whether it appears in second order derivatives or first order derivative, these three are of second order derivatives, and P, Q are first order derivatives. All the coefficients appear are constants only. With that, another thing is to notice that powers of each derivatives only one. Okay, so that's why it's this dash is not dash, basically this is I'm writing 1. Okay, 1. So all of power of the highest order derivative is 1, so that's why it's linear also. So this is the general form. Now in today's lecture I will be only considering linear homogeneous equation. Homogeneous means, in this equation, homogeneous means, let me write homogeneous only when this right hand side equal to 0, that is g equal to 0. So I will discuss how to solve homogeneous second order linear partial differential equation with constant coefficients. I guess it's clear. Okay, so let me take an example. This is the problem. Solve del 2z del x2 minus del 2z del y2 equal to 0. Okay, let me take black. So let me write the solution here. So in order to solve this kind of second order linear PDE with constant coefficient, we have to take trial solution. The concept of trial solution was also introduced to you definitely at your UG level, or maybe someone already had it in your school calculus also. In the case of ordinary differential equations with linear and constant coefficients. Okay, suppose you are having your problem like d2y dx2 plus 3 into dy dx plus y equal to 0. So in this kind of problem you also consider trial equation as you remember, y equal to e to the power m into x. So now this trial equation, in this case the trial equation must be changed since this PD. For this case we have to take the trial equation as, let me start here, let phi, okay, that's z equal to some phi of y plus mx be a trial solution. Interesting. So as you all know, this phi is any arbitrary function of y plus mx. Okay, you know the PDE can be formulated, as I have discussed in the previous block only. PDE can be formulated by eliminating arbitrary functions also. So trial solution of this type is justified. Now I will find zxx and zyy and I will put it here to get the value of m. Okay, so let me show how to do that. First find out therefore del z del x, that will be definitely m into phi dash of y plus mx. Similarly del 2z del x2 will be m square phi dash of y plus mx. Again del z del y, what that will be, this is y, what that will be, that will be phi dash of y plus mx, and this will be phi double dash, I'm sorry, and finally you will find del 2z del y2 as phi double dash of y plus mx only. Okay, now I will substitute these values to this equation, name it as 1. Go to the next page. Okay, then from equation 1 we get what we get, we will get, let me see this again, otherwise, okay, this m square into this and this will be, okay, right, m square phi double dash y plus mx minus phi double dash y plus mx equal to 0. Now in the next line we just simply factorize, okay, take this common, phi double dash y plus mx, so you will get m square minus 1 as a factor of it. Now you have to assume, I mean we are assuming that this is assuming, I'm writing it here, you will get it I guess, phi double dash of y plus mx non-zero. Then what will be your m? Plus minus 1 only. Okay, so this equation, let me take another color so that this equation known as auxiliary equation. Okay. Okay, so these are the roots for auxiliary equation, plus minus I. Okay, so the solution will be, then the solution to the PDE1 is phi is equal to phi 1 of, just second, phi 1 of y. First you have to take the value of m to be 1, then if you take m1, then y plus x, and another function is, oh, that will be phi 2 of y minus x, where this phi 1 and phi 2 are two arbitrary functions. That also you have to write, where phi 1 and phi 2 are arbitrary. I'm writing it here only, functions. So I think this is clear to all of you. So first you have to find out the auxiliary equation, then find the root of it. Since this is a second order PDE, then the auxiliary equation will be also of quadratic form. It will possess two roots, and according to the roots you have to finally conclude the solution. So let me give you another example of third order PDE. Okay, so that I will be directly show to you. Okay, third order PDE with constant coefficient. I am not restricting myself in second order in this case, because this is of constant coefficients only. So whenever it is of constant coefficient, you can go up to any order, okay, as long as you can solve the auxiliary equation. So that's why I am taking this example. So this is solve. Let me write it in this form, d cube, that's mean third order derivative only. I hope all of you are familiar with this kind of notation. D square d dash plus 4 into d dash square of z equal to 0. Okay, so as you can see, since it's d cube means nothing but, I mean here this d means del x and d dash means del y. Now everything must be clear to you, or if it is not, then allow me to write. That will give you del cube z del x3 minus 4 into del cube z, and that is del 2x del y plus 4 into, what that will be, that will be, sorry, del 2 del cube, ultimately I'm sorry, del cube z divided by del x del 2y equal to 0. I hope this is clear to you. Okay. Now, as you can see that this is a third order PDE, and I don't want to confuse you with this notation. You all know, I guess. So let me erase this portion and let me proceed to solve. Okay, the interesting part. So solution. Let z equal to phi of y plus mx be the trial solution of this equation, name it as 1 of 1. Okay, then I can directly write the auxiliary equation. Then auxiliary equation of 1 is m cube minus 4m square plus 4m equal to 0. I mean, informally the technique is you simply replace d by m. Okay, this is the technique, and you will get the auxiliary equation. Now this is a cubic equation, and you need to solve it to find the root. So take m as common, so that will be m square minus 4m plus 4. So ultimately you will get m into m minus 2 whole square equal to 0. So it has 0 as its one root and 2 is repeated. So 2. So this is a new case where you can see that we have repeated roots. So what to do when we get repeated roots? How to write the general solution? Let me write it here. Then the general solution is z equal to, okay, the first arbitrary function is phi 1, and where I have taken m to be 0, so phi 1 of y only. The second one is phi 2, and where I have taken the value of m to be 2 only. Now 2 is repeated, so the other one and the last one will be written in this way, plus x into phi 3 of y plus 2x, where this phi 1, phi 2, phi 3 all are arbitrary functions. So this is the case when your roots are repeated. Also this is third order PDE, and I will be considering another problem with fourth order. Okay, so the case becomes more interesting. So let me write the problem. To write the problem, let me take another color. Solve the differential equation d4 minus d dash to the power 4 is d dash to the power 4 of z equal to 0. You all know, as I just said, d is nothing but del x and d dash is nothing but del y. Okay, let me solve this. The auxiliary equation is given by m to the power 4 minus 1 equal to 0. As I have just told the technique, you have to simply replace d by m. Okay, so before that you have to write that let phi of y plus mx be the trial solution. Okay, so after that you will get the auxiliary equation like this. So m is the fourth roots of unity. So these are 1 minus 1 I minus I. So right now it has complex root also. Then how to do and what to do. But one thing you can notice here, all the roots are different, no repeated roots. So in this case the solution is very easy. You simply write the general solution of the PDE is z equal to phi 1 of y plus x plus phi 2 of y minus x plus phi 3 of y plus the m value is I into x and phi 4 of, okay, let me write it in the next line here, phi 4 of y minus I into x, where this phi 1, phi 2, phi 3, phi 4 all are arbitrary functions. Okay, so this is how to solve a second order partial differential equations with constant coefficients, and this is the case of homogeneous second order partial differential equations. Okay, right hand equal to 0. So in the next video I will discuss what will happen for the non-homogeneous linear second order partial differential equations with constant coefficients. So there are many conditions, like it has to be linear with constant coefficients and non-homogeneous. So I will discuss in the next video. Thank you for your kind attention. Let me stop here. Please follow the next video.